Okay, so we have the physical layer. Let's check the intellectual layer. Or intermediate layer for the connectivity, we use tool ping to check connectivity. And of course, the packet that goes outside is named ping, and the returning packet is called pong. Well, let's say how it works. Ping. First is always slow. Ping, 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 ping. Great. We can go. So my name is Konrad Gawda. I came here from Poland, and I work on every day for Orange, the telecommunications operator, but I work there as a cloud evangelist. And you might ask, well, what the hell Orange has with clouds? Yes, we do have our own public cloud located in Poland in our data center. If you need virtual machines in Orange data center in Poland, just ask me. Yeah, and okay, that's about me, and that's the bytecode. And I made it green like matrix style on purpose because it's hard to understand. And it looks a bit like assembly language, but it's Python, and it has disadvantages of both. I mean, it's hard to understand, but still has the performance of Python, not assembly language. But how it works, let's start from the beginning. So here we are, a happy Python developer. Then there is a Python binary, Python interpreter executable that we will use. We'll put our Python code into it, and it happily will interact with the world, with console, disk, network. It will do stuff what we want. That's basically it. But what happens inside? Well, it turns out that Python has a virtual machine. So if you know that Java has virtual machine and Python is different, no, Python also has its own virtual machine. And do not confuse that with cloud virtual machines. That's the different thing with the same name. So, but the virtual machine is basically the core of the interpreter. It does stuff and like the interaction with the external world. But before it kicks into the game, there is a compiler, which uses, for example, abstract syntax tree to parse your code. And there is an intermediate step between them, and this is the bytecode. So bytecode is a language used for intermediate step between Python compiler and Python virtual machine, so basically interpreter. And do not confuse that with machine code. Like in your computer, you have a processor CPU that is playing with machine code. And in this case, machine code is in Python executable like Python exe. That is the machine code, that those are instructions for your CPU. Bytecode is a different thing. It's built with instructions for the Python interpreter. So two separate things. But as I said, there are some instructions. So what are those? Well, here they are. So basically, I will now spend most of my time explaining each of those instructions in detail. Well, happily not. But if you would like to see all of them and the source of truth, well, that's the Python C code that's on the GitHub, and there is a big switch with all the bytecode instructions. So when you run Python mycode.py, you execute that. Well, first it produces the bytecode, and then this machinery kicks in to do things that you've described. Okay, so let's see some examples how it works. And here is a basic function to start with. So adding the numbers seems fairly easy. And let's see what can we do from inside of the interpreter. What is exposed to the language itself? So of course, add is a function, so it's an object. So it has some methods and some fields like dunder code. Well, that's a field. And what's inside?
If you open editor and do auto completion, it will show you the following fields. So I've printed them, including the values that they do have, and some of them may be interesting for us. So, for example, var names, we see that there is variable A and variable B. Name and qual name, we see that the function is called add. There are some flags and so on, but the most important thing is that one. That is the code. That is what your function is doing. And it's, of course, gibberish. Doesn't make a sense if you see it as numbers. It's a byte string. But happily, there is a tool that will help you understand what's inside. And it is called this, not this. So it's a great pronunciation exercise if you give this talk to someone. So you import module called this, and it has a function show code, which shows you perfectly everything besides the code. Perhaps that's why they also introduced the name code info. There are two names for the function. So it shows you all of that, besides the code, in a user-friendly manner, at least programmer-friendly. Okay, so you, for example, see the flags and how to understand the flags. But what about the code itself, the bytecode? Well, it's this.this. Yeah, good naming. Okay, but finally, we've got a bytecode that we can see and understand. And in fact, the real bytecodes are those things in yellow. Things outside is just explanation for you as a human to see what's inside. In fact, that's not always this. That's not always this. It depends on your Python version. So in different versions, you will get different bytecode because bytecode changes with minor Python versions. And that's important to remember. So I'll try to give you the number of Python that I am showing the examples with. So, but coming back, this one just prints the information. So it's a quick and dirty thing. But if you would like to have a more Pythonic view on those instructions, then you use get instructions. Finally, good name. So it gives you a list of objects. Each of them represents the bytecode instruction, and you can see what's more or less what the objects are containing. Okay, good enough. So we already know how to get into the details of a function that we write. So let's get a bit more complicated function to use some arithmetics and some module and some function from that module. So just to have it handy, the code is here. So let's see this.this. By the way, and on the top, you've got the numbers. If you like the numbers, you can decode them in your head. But that's the printout. And before we start executing that, let's understand how it grabs the things from the memory. So those are the things you've seen from the previous function that are in the fields of the code object. And the instructions will be getting things from there. So let's see, for example, load const. Okay, it loads some constant. And by the way, so it tells us that the function will have a place where it stores constants that it will use. And for example, this half is a float that, well, it will not change, so it's a constant. And there is a tuple with constants that will be used. Index 1, that's a half, so you have half here. That's how it works. So then, again, load global, just forget the null for now, load global. So from globals, we will load something, and it is under name math.
And again, it's index. Wait a minute. What is in under index 1 here? Is it math or SQRT? Okay, so why the hell it is 1, not 0? And then load attribute, this has 2. There's no index 2 here. Out of bounds exception. Well, if you dig into documentation, and by the way, the documentation for the bytecode is located in the documentation of this module, you'll see that they divide that by 2, so shift right by 1, because the lowest bit stores some other information. So in fact, this counts for index 0 and this counts for index 1. That's the trick here. Then load fast. So we are loading something from the variable x, and the name of the variable is taken from var names, and this time no tricks with the indexes. Store, so store under the variable name. Okay, load fast, so load into something from variable named y. Okay, I think we know more or less how, and this is all how these arguments in bytecode translate to meaningful values. Okay, so soon we will execute that code, but before that we need to understand where it is loading and from where it is storing. What's our playground? And that's the point where stacks come in, and there are frame stack, evaluation stack, and also block stack. So each time you call a function, a frame is created on a frame stack or on a call stack, and here is like that will be perhaps your main function. That will be a function that you call from a main. That will be another function that you call from that one, and that will be yet another function, for example, the math.sqrt. And if a function ends, then the frame is removed. Okay, so those are the frames. And let's take example of one function that is executing, let's say, right now. It has 2 stacks. The evaluation stack that will be useful for us, because that's where the bytecode is loading and storing things, and a block stack which basically keeps track of the indentation. So if you were wondering how the Python tracks whether that block of code, what was the previous block of code indentation, how many space bars, well, that's it. Okay, so this will be our playground, the evaluation stack. Okay, so be prepared and bear with me. So we have our bytecode, and the first instruction comes for free. It's already executed because it does nothing. Great. Okay, the next one says load const. So bang, it loads a constant into our evaluation stack. Next thing also loads a thing into our stack, and because it's a stack, a new thing will appear on top, and then a new thing will appear on top, and so on. So bang, and I will not explain the null, so just pretend you don't see that, because we have limited time, so just forget about the null. But we have some things that appear on the top of the stack. But then load attra will be executed, and it has the argument of SQRT, but it will int something from the top of the stack. So basically it will int that value, and this is a math module that is a Python object that is loaded on the stack, and the instruction will remove that and exchange it with math.sqrt. Ready? Done. Okay. What's next? Load fast from variable y, and variable y was our argument. So we have it. This was called with x equal to. Okay, so we have that, and now now, yeah, you see that was the building the tension for for instruction call. Instruction call, but it has only one argument. It only says call one. So why the hell we need to, okay, we will be calling a function, but we need to know what function to call and what arguments to push there. Well, and we have only one clue. One says there will be one argument. So, okay, there is one argument. That makes sense. But in fact, the instruction will eat number of arguments, so one argument, that. Then call will eat the pointer or Python object that is representing the function to execute, and it will also eat null, but forget about it. Okay, and so it will take those, execute some function in the separate frame, and we'll get from top the result. Okay, and we've got result here loaded on the stack. So now be prepared, because something will also happen very quickly, because we'll call binary operation, and it doesn't mean it works on binary numbers. It means that it's a binary operation, so has two arguments, and it's operation number 5, multiplication. Be prepared. So it removed the arguments and put the result instead. Ooh, so we're close to the end. Okay, so now we're storing the thing that we have on the stack into variable y. It's gone. Okay, and if you sometimes wonder whether dividing this into two different lines has some influence on the code and would just return be the same or not, well, you have explanation here. So we've saved something into variable y, and then we're moving into next Python line, which says load from the variable y and return that. Done. Yeah, ladies and gentlemen, we are done with executing our function. So now you know how the bytecode works. So yeah, that was the hard part. So now what we can do with that? What's the influence on us? So basically, this part, the compiling, takes some time. So to save that, the intermediate step is saved into PYC files. So it's crucial. So sometimes the Python executable will skip that part with the compiler part as long as the PYC is up to date. But it's crucial to know if the file is up to date. So how the file does look like inside? Well, you have a magic number, a bit field, source timestamp, and source size. And this will be compared to check if the PYC file is up to date. There is also another format with hash value instead of date, but it's rarely used. By the way, if you're wondering about the magic number, here are the magic numbers, and you can get them from importlib util. Okay, and that's let's see then when the files are created. Well, in fact, they're in Python 3 they are created under PyCache directories, and they're created on import. So when you're importing code, they're created on pip install. Also, standard Python library comes with those files pre-compiled, and you can create them manually. So you have the commands to do so. And let me just run this command, and a new directory is created, PyCache, and it has the file, which also has the Python version in it, just because the bytecode changes between Python versions. So that's why the 312 here in the name. And each time some code will try to import test py, interpreter first will try to use that file. But funny thing, you can also execute that PYC file directly, and it's a legit thing to execute with Python. Some takeaways here. Pip install creates those files. UV does not, at least last time I've checked, but it's still a fresh tool, so please check that if your logic depends on that. Avoid unneeded imports because you're generating files that may not be needed. And I think that, okay, I guess that's the most important, the most useful thing from this talk is if you're preparing a Docker file and you just simply copy the code there, you're not preparing a package that you will pip install inside, you're just copying the Python file, then run inside on the Docker file level Python -m compile all dot. Dot means the current directory, and it will recursively go and compile, so create PYC files for all the Python code inside. So you save time on the execution because Python will not have to do that on executing your Docker file. Okay, great. I said about those PYC files, but I tricked you a bit. I only said about the header, but what's the real thing inside of it? Well, there are objects in Marshall format. Marshall format, what the hell is that? Well, if you check the documentations, it's undocumented on purpose. So here be dragons. But still, even if it's not documented, there is a Python module to play with that. And you can open the file in binary mode. You just need to skip the header that I've told you before, and you can use the Marshall module to load that. And it says 16, that's a printout from SIG. And you get an object, and it's a code object. So basically, that's what Python interpreter does. You rarely need to use that. But in fact, so if we take the M object and import function type, you can create a function with that code, execute it. Well, it does the job. So here is the way to execute a PYC file directly from Python level. Okay, but there are other useful things there. Optimization, that's a thing that has several meanings. But one of them is on the step of generating the bytecode, so compiling. And for example, if you do compile all, you can select the level of optimization in the meaning of generating the bytecode. And it will create files with different names representing different optimization levels. And what are the levels? 0, no optimization. 1, asserts are removed. 2, docstrings are removed too. And you can also do that directly just running Python executable. So if your business logic depends somehow on asserts or docstrings, well, be aware. And that's a thing that was here for a long time. Okay, exception handling, that's also a field where bytecode may be useful. I've just generated some exception. I hope you see what's happening here. And in fact, if I call this without an argument, it will grab the latest exception that has happened. Or otherwise, you can just say this.tb, like traceback, and give it a traceback to analyze. And well, I don't know, perhaps it may be useful one day. But I would like to show you one thing that's, I don't think it's useful. It's hardly useful, but it's cool. So let's try building a function on the fly. So we will need some classes, and perhaps you'll need a code type, not for the kind of heart. But I will use its neighbor, which is called function type. I've used that a moment ago, but this time, remember the add function? So first step, I'll just try to copy the add function, taking its code, and here the empty dict is globals. Okay, and I'm executing that. And what will happen? Well, exception, because the add function needs A and B to add. Okay, sorry for that, so let me correct myself. And yes, we do have results, so that works. Okay, and the code object has a replace method that works more or less like for replacing in strings. So here you will have a code with replaced things, but no replaces here, so just do nothing replace, and it works. Okay, so let's do something. Let's replace the var names. Let's change them from A and B to X and Y and try to execute. Oh, but I didn't give any numbers, but it says there is no X, no Y. If I give it, it works. Okay, but I'm not really interested in var names. What I'm interested in is code. So just to have a cheat sheet, here is the CO code from the add function, and I will create a function with one number changed. Okay, and you remember previously the result was 5. Now it's 2. And in fact, I did a bit of research to find that this specific integer represents the operation of multiplication. So it's not multiplying, of adding. That was sum plus. So it's not plus, it's something else, and that gives you 2. And that's a question that you may now start thinking of. What kind of operator is under number 1 that gives as a result 2? Okay, in the meantime, what would be the other operators? So I'll just loop through different values and let's see what happens. And well, it goes quite well, and then it says, well, unsupported operand between the integer. In Poland, we call this małpa, monkey. I know it's German, it's Klammeraffe. And in Italian? And is it also monkey? No. Snail. Ah, beautiful, beautiful. Okay, so you see that under the 0, 1, 2, 3, 4, under number 4, it's the snail. Okay, so add exception handling, and you've got all the possible results. Okay, so now to show the results of the question. So what was causing this? What was resulting in number 2? I will now dig into get instructions to print the operator's meaning, and you see it was ampersand end, so binary end. So as you see, you can play with that, and I think you may find a way to use that for optimizing some functions. People used that to introduce f-strings before f-strings were a thing. So perhaps in the future you will find how to leverage that, writing some decorator or whatever. Okay, and if not, then I just hope it was interesting. My name is Konrad Gawda, and here is a shameless plug for the PyCon Poland.
One question about the stack part. What happens if you import a sqrt function at top level? I imagine it changes the bytecode order of things.
Okay, so basically, if the bytecode instructions, well, they're trying to get something that is not on the stack. That's no. I'm still compiling the question. For sure, if some errors appear, I mean, if, for example, that SQRT would not be there in the module. Okay, let's go back. We'll get there soon. Up.
Yeah, imagine that you have a line before that. From Mac to points.
Ah.
Change the order of the.
Okay.
Just involve this part inside.
Okay.
So see that the line 4 was global. It's trying to import at this time the function from the model.
Okay, now I see. Okay, so before running this, of course, you see that this is a line. Okay, before that, I did import math. So of course, otherwise the code would break. And then if I did import, then math module is inside globals. So load global can reach for math. If I would make from math import SQRT, then SQRT would be in globals. And okay, I wouldn't need to write math.sqrt because math would not be in globals, but just use directly SQRT, and that would be loaded directly from globals. Pardon? Yeah, then it wouldn't be needed. Load attribute, yeah, and yeah, that wouldn't be needed. Shorter code, one bytecode instruction faster.
Okay, we are out of time. So thank you again, Konrad.